You ask it a question. It answers in less than a second. The words feel thoughtful, they feel considered, they feel almost human. But nothing human just happened. What you got back was not a thought, it was not an opinion, it was not understanding. What came back was something far stranger. And once you see how it actually works, you will never look at AI the same way again. Let's start with the word that causes more confusion than any other in this conversation. Intelligence. When you hear that word attached to a machine, your brain immediately reaches for a comparison. It compares it to you, to your memories, your feelings, your inner voice. But that comparison is the wrong one to make, and making it is the reason most people fundamentally misunderstand what is happening when AI responds to them. Here is what is actually happening. Every large language model, the kind powering the AI tools you use today, was trained on an enormous amount of text, books, articles, websites, conversations, code, billions and billions of words, scraped and collected and fed into a system over months. During that training, the model was given one task: predict the next word. That is it. That is the whole job. Given everything that came before, what word is most likely to come next? It did this trillions of times, and each time it got it wrong, its internal parameters, the numbers that define how it processes information, were adjusted slightly. Over time, across billions of examples, those adjustments accumulated into something remarkable, a system that could predict the next word with extraordinary accuracy, not because it understood what the words meant, but because it had learned the statistical patterns of how words relate to each other across virtually every topic humans have ever written about. This is what researchers call a transformer architecture. It was first described in a landmark 2017 paper by Vaswani and colleagues at Google titled "Attention is All You Need." The key innovation was a mechanism called attention, a way for the model to weigh which words in a sentence are most relevant to each other when predicting what comes next. Your name matters more than the when a sentence is about you. The model learns to know that. So when you type a question, the model does not search a database. It does not look anything up. It does not reason through possibilities the way you might. Instead, it reads every word you wrote, weighs each word's relationship to every other word, and then begins predicting, one token at a time, what the most statistically likely continuation of your input would be, given everything it learned during training. A token, by the way, is not quite a word. It is closer to a chunk of a word. The word thinking might be 2 tokens. The word AI might be 1. The model processes everything in these chunks, not in whole sentences or whole ideas. Now here is where it gets strange. The model does not generate your entire answer at once. It generates 1 token, then it feeds that token back into its own input. Then it generates the next token, then feeds that back in. Over and over until it decides the response is complete. Every single word you read in an AI response was generated 1 piece at a time, each piece influenced by all the pieces before it, but none of them planned in advance. There is no internal draft, there is no mental outline. The model did not know how its sentence would end when it started writing it. It found out the same way you did, 1 word at a time. Yoshua Bengio, one of the pioneers of modern deep learning and a Turing Award winner, has described this as a fundamental limitation. The model, he argues, lacks what he calls systematic compositionality, the ability to take learned concepts and recombine them in genuinely new ways the way human reasoning does. What looks like reasoning is pattern completion, very sophisticated, very fast, very impressive pattern completion. But pattern completion is not nothing, it is in many ways extraordinary. Because the patterns the model learned are not just surface patterns, they are deep structural patterns, patterns of argument, patterns of explanation, patterns of cause and effect. When you ask it to explain something, it has seen millions of explanations, good ones, bad ones, clear ones, confusing ones, and it has learned through all that prediction training what a good explanation looks like structurally. So it produces something that looks like a good explanation. Because statistically, that is the most likely thing to produce, This is why it can write poetry, debug code, summarize a legal document, and then immediately switch to helping you plan a birthday party. It is not switching between different skills. It is applying the same underlying mechanism, predict the most likely next token, across wildly different contexts. The training data contained all of those things. The patterns are all there.